In this lecture, we're going to be talking about name scopes and bindings. And a good source of reference material for this lecture is both the Scott text, Chapter 3, and also my notes with name scopes and bindings. And we're going to start out with a few definitions. And we're going to start with what is a name. And a name is an identifier that allows us to refer to variables, constants, functions, types, operations, and so on. So a name could be a type like int in C or Java. It could be a variable name like miles per gallon. It could be a function like compute miles driven. Then a binding is simply an association of a name with an object. And that could be a allocation of an actual integer to some variable, or it could be the allocation of a heap allocated object to a pointer variable. It could be the association of a label in a language with some memory address, so you could use a goto statement, obviously a bad thing, but that's another example of a binding. And then scope is the lifetime of a binding of a name to an object. So for example, local variables, they come into existence at the time that a function is called, and at that point, for example, local parameters are bound to values, and then they die at the time that the function exits. And if the function is recalled, they come back to life, but that is that's in a different, it's a new binding of that name to a new object, and it's done through a different stack frame. And finally, we talk about the referencing environment as being the complete set of bindings in effect at a certain point in a program. So example, if we're in some function, not only do the bindings for the local variables and parameters in that function exist, but in C and C++, you would also have global variables. In a method, you would also have instance variables that were live at that point in the program. So you'll often hear about different times that you can have for binding times. And the different times, we can start with language design time. So we'll say binding times. And the first thing is at language design time. So at that time, reserved keywords are an example of bindings that are made at the time that the language is designed. Certain constructs like for loops, if then else, those constructs are in some sense objects. They're control constructs. Those binding decisions, how they're going to be structured, are made at language design time. Then you have decisions that are made when the language is actually implemented by a compiler writer. So compiler implementation time would also be considered the time at which the compiler is being written. And examples of decisions made at this time might be the number of bits that are allocated to different types. So for example, you might say that a long int gets 64 bits, an int 32, a short 16, an unsigned also 16, so on and so forth. You also at this point might decide on the maximum sizes for the stack and the heap, or how you're going to handle runtime exceptions such as arithmetic overflow. Are you going to make it a catastrophic error that cannot be recovered from, or are you going to make it an exception that can be caught and handled by a user program? Next, we have compile time. And bindings that occur at this time are things like associating constants with or values, constant values with their variables. You might also have the allocation of stack frames. These are done, their layout is done at compile time. Functions whose address is unambiguously known because it is within the same file as the calling function, that can be determined now. So an address, if we're in some file, say bvz.cpp, and we have some function b and another function a, and let's say that b calls a, well, because A is in the same .cpp file, the compiler can determine the address of A and assign it at that point. So that's a binding of the function address to the function call. Then you have link time. And at link time, you may have other bindings made. So if A over here had been declared in another file, say foo.cpp, then it wouldn't be until link time that you might be able to fill in the address of the function call. So in this case, it would be a link time binding between this function call here in bvz.cpp and the time when it gets an address. Then we have something called load time, and this is when the program is physically assigned memory or assigned physical memory. And at this point, you actually have another kind of binding. At link time and compile time, this function address perhaps was simply shown relative to some offset, say from the beginning of the file. Now, at load time, you may actually be assigning a beginning location to that file by storing that beginning location in some register. So now there's a binding of where that program starts in memory with a register which has that actual starting location. Then we talk about runtime, when the program actually starts running. And then you may have bindings such as the new operator being called and allocating something off the heap and assigning that object to a pointer variable. That's a dynamic binding. Or virtual method calls cannot be determined. Where we're going to jump to, which virtual method we're going to jump to, cannot be determined until runtime. So that's a dynamic binding for virtual methods. So we talk about basically link through, or language design through link time as being static binding. And we talk about load time and runtime as being dynamic binding. Okay, because static binding is stuff done before the program starts executing. Dynamic binding is done as the program starts executing. And static binding, those bindings refer to every execution of the program, whereas dynamic binding specifically refers to the binding that occurs during a single instance of the program. And in general, dynamic binding leads to greater flexibility, whereas static binding leads to faster code. So we say static binding gives us faster code. As an example, with functions, if we can bind a function call at compile time, we can jump straight to that address at runtime. So that's faster. Whereas with a virtual method, we have to go through a jump table, through a V table. That's slower. However, the virtual method gives us greater flexibility because it allows us to defer until runtime the decision as to which method to call. For example, with graphical objects, if we want to draw different graphical objects, yet not have to worry about which draw method gets called, there's a lot greater flexibility with dynamic binding at allowing us to defer that decision about which draw method gets called until runtime. So that takes care of names and bindings, two of the three things we said we'd talk about in this lecture. Now we move on to scopes, which is going to take a fair amount of time to discuss. Remember, scope refers to the lifetime of an object, when it's visible and when it's not. And there's two ways that we go about determining scope. One is at compile time and is called static scope. So let's just write scope here. And we have two types, static scope and dynamic scope. Okay? Static scope is determined, the scope of a variable is determined, can be determined at compile time. And with dynamic scope, scope of a variable is determined at runtime. Now, some variables, you always can determine their scope. And that is true of local variables and parameters. Those variables, you always know their scope as being limited to the lifetime of a function. But what happens when you have a non-local access? For example, to a global variable in C or to an instance variable in Java. In that case, the variable is not declared within the function, and instead the program somehow has to determine which name we're referring to. And sometimes there may be multiple names available, and we have to figure out which one. So it's kind of good to work with an example here. So let's just write a sample program. We'll define a global variable temp, and now we'll have a function foo, and some languages have nested functions, among them Python, ML, Scheme are some. So we're going to define here some nested functions, and within goo we're going to have a temp variable, and we're going to assign it the value 5. Then we're going to call BVZ, and here we're going to have a function BVZ, and we're going to assign it the value 6, and then we're going to call goo. And the question is, when we execute BVZ, what temp is going to be assigned the value of 6. You can see that there are two values of temp that have been defined. One is the global variable and one is this local variable. And it turns out the answer to this question depends on whether we're using static binding or whether we're using dynamic binding. So let's first assume that we are using static scoping. I'm sorry, I said static binding, but I meant to say static scoping. So if we're using static scoping, what that means is that the reference to temp is in the closest enclosing block. So I'm going to say look for the variable in the most, for a definition, which I'll abbreviate as DEFN, definition of the variable in the closest enclosing block. So in that case, the closest enclosing block is this global reference for temp, because it's not defined here, it's not defined in foo, which is the next enclosing block. Therefore, we go to the global value, and that's the value of temp that is altered. By contrast, when we use dynamic scoping, then we look for the definition of the variable in the closest stack frame. And if you look at the sequence of calls here, we started with goo, and then we called, from goo, we called BVZ, and down here I'm going to have globals because they're global. So in this case, the closest definition of temp in the stack frame is in goo. So using dynamic scoping, we're going to modify this value of temp. So dynamic and static scoping lead to very different results. And when languages were still being actively experimented with, language features I should say, back in the 70s and 80s, there were major languages like Lisp would use dynamic scoping, whereas C would use static scoping. It's now been pretty much established that dynamic scoping is dangerous and leads to unexpected results. And so almost every modern language uses static scoping. Now, the reason that dynamic scoping is so dangerous is, let's look what happens if I actually I'm a code maintainer. So I come in later and I'm maintaining this code. Okay? Let's see what happens when we add a new function as a maintainer. Let's say that we decide that we're now going to call a function called boo from goo, and we'll define it up here. We'll say void boo, and because we need a temporary variable, we put in int temp, say we set it to 10, and now we do some stuff and then we call BVZ. So we still are calling BVZ, but now we're doing it from within boo. Well, now our call stack, if we look at it, is globals. Goo got called here. Goo called boo. And boo called BVZ right here. Okay, well the problem with calling BVZ there is that boo just defined a new thing of temp. So the original designer of BVZ was assuming that we were going to be changing the temp in goo. However, the code maintainer came in and, not realizing what was going on, inadvertently created this temp variable for boo. And now when I execute temp equals 6 here, I end up modifying this version of temp rather than this version of temp as the original developer of the code intended. And this will break the code in all likelihood. And because this tends to happen fairly frequently, it quickly became apparent that dynamic scoping was dangerous for longer-term maintenance of programs, and therefore it no longer is actively supported in modern languages. Now, in addition to this idea of static scoping and dynamic scoping, there's other references that you may make to non-local variables. You've seen that in when you're doing classes. If you have a class and you have a class, say widget, and it has a variable, say a, and within some function within widget, like say get value, you may say return a. Well, that's a reference to a non-local variable, and as you all know, it first checks, in this case when you're in a class, the rule is you first check for instance variables if the variable is non-local before you go looking for global variables. You've also in this course seen how Java allows us to create nested inner classes. So I can have a nested inner class that, as an example, add a mouse listener, and we say new, say mouse adapter. And within it we may have public, say void mouse pressed. and I'll abbreviate, well, I'll just say mouse event E, and then I might say A equals 10. Okay, and in this case, the reference to A is actually a reference to the variable A in widget. And what happens is that first, Java is going to look in the inner class to see if it can find a val or declaration for A. It doesn't find it, so then it goes to the outer class, which is widget, and finds it. So this is another example of having to determine the scope of a variable. In this case, for inner classes in Java, the scope that we look at first is the outer class before we go looking for global variables. And as yet one more example, with inheritance hierarchies, let's say we have class widget extends, say, component. And let's say that we had not declared A here, but let's say it was declared in component, then we would actually, or the compiler would actually go chasing up the inheritance hierarchy for widget, looking for an instance of A, before it would go looking to global variables. So you actually, when you're looking for a non-local variable, a lot of it depends on which language you're in. If you're in C, it's pretty easy. You essentially just look in the globals. If you're in C++ and you're inside an object, let's say you're in a method, then you first look at the enclosing class. Then you would go up, you would look in superclasses, and then you would finally end up looking at globals. In Java, if you were in an inner class, so we'll say a method in an inner class, then you would first look at the enclosing inner class for the non-local variable. Then you would look at the outer class, and then you would chase superclasses for the outer class. So you chase superclasses for the outer class. And then you would look at globals. And in fact, I missed one step here. You would first look at superclass. Here, you should actually look for superclasses for the inner class before you go looking at the outer class. So there are, in this case, 1, 2, 3, 4, 5 different places where the Java compiler would go looking for its variables. The next thing we need to talk about is what happens when you are allowed to have what we would say are undeclared variables. And this happens all the time in scripting languages and some functional languages. So for example, in Python, I'm allowed to say something like def function, and I might say A equals 10, B equals 20, return A plus B. And the question is, what is the scope of A and B in Python? Well, in this case, it is a local variable. But if this were Perl, interestingly enough, A and B would be considered global variables in that case. And their scope would be, they would exist even after the function had exited. So if outside this function in Python, if I were, this is pseudocode now, say to print A and B, I would get an error message in Python because, as you probably would expect, A and B are local to the function. But in Perl, if at this point I printed A and B, I would actually get 10 and 20 as the result because A and B persist after I use them or after I assign them values in Perl. So notice here I never declared them. They in effect got declared at the moment that I assigned them a value. Now in Python, if I really wanted to refer to a global, then I could say global AB, and now presumably somewhere in Python, maybe here outside the function, I'd written A equals 20 and maybe B equals 40, and it would be modifying these global variables instead of creating local variables. Similarly, in Perl, if I use my keyword and say A comma B, that will declare the variables locally as local variables rather than as globals. And so down here, when I now print AB, I will end up with an error message. For those of you who've done a bit of Perl programming, you'll also know it's possible to declare local variables using the local keyword. But what you may not know is that in this case, local means use dynamic scoping, whereas my says you want to use static scoping. And static scoping is what we prefer. Unfortunately, Perl started with dynamic scoping, and therefore, when it introduced the local keyword to make a variable local, it still was saying these variables would be dynamically scoped. Later, when it became apparent how damaging dynamic scoping is, they went back in, the developers of Perl, and put my in as a way to declare a variable as local, but using static scoping. Okay, so that takes care of scoping, and now we're going to move back to another binding issue, and that is issues that are associated with something called aliasing. So aliasing, its definition, is where we have more than one name referring to the same object. And pointers are the most common way we introduce aliases in a language. And even though Java doesn't have pointers, it has references, and you can easily end up with references to the same object in Java. And pointers obviously introduce both power and problems in languages. Many of you are aware of having dangling pointers where you accidentally deallocate some memory while you still have pointers pointing to that memory. Now they're dangling, they'll go into that memory later and potentially wreck your program because they'll overwrite memory that's now been allocated to someone else. Conversely, they can lead to memory leaks if you forget to reclaim memory after the last pointer to an object has been deleted. And they cause problems for compilers with optimization. So I'll say they limit optimization opportunities. And as an example of how they do this, consider the following short program fragment. So I'm going to declare A and B as well as pointers, P and Q. I'm going to say A equals star P and star Q equals 3 and B equals star P. Well, on the face of it, it sure looks as though we could assign the same value to A and B. And a compiler would dearly love to do so. If it were generating code for this code fragment, what it would really like to do is something like, say, load, say, register 6 with the contents of P, store register 6 to A, do something with that Q, and then store register 6 into B. That's a pretty nice optimization. We avoid having to read the memory for star P a second time. The problem is that we have this intervening reference that says star Q equals 3. And let's suppose that there was code earlier that said that P equals the address of X and Q equals the address of X. And further, let's say X was equal to 8. Well, now you can see there's a problem because based on this, we have P and Q as aliases for X. So X is initially 8 when we get to this statement right here. And A should get the value 8. But now when we execute the statement star Q equals 3, we're going to end up assigning the value 3 to X. And you can see that B should get the value 3. And this code that we just wrote here is now broken because of what happened with 3 being assigned to star Q. So aliasing creates some nasty problems for compilers, and for about 20 years from the start of their introduction in the early 80s in the C language to the early 2000s, compiler writers were really stymied in their ability to optimize programs. Now, this proved to be a fruitful research area, and ultimately compiler writers have developed what are called powerful data flow techniques that allow them to trace how execution is flowing through a computer, and they can figure out when the reference is going to be dangerous or not. So in this case, there's kind of this idea that, okay, X has both pointers from P and Q, and we tried to assign A value from P, star P, and from star B. But because there's this intermediate assignment to Q, it's going to cause this problem with B. B is not going to have the same value as A. And you can, as I say, use some sophisticated data flow techniques to tease out the fact that in this case A and B are not pointing to the same, or that, I'm sorry, that A and B should not get the same values. Now sometimes there's not really a way to resolve the situation at compile time. If I were to say if Y is greater than Z, Q equals ampersand X, else, let's say Q equals ampersand Z. Now, depending on how this if-else works out, Q may or may not be pointing to X, and there's no way, in fact, that a data flow analyzer is going to be able to figure out whether it's a safe optimization to make register 6 store into B unless it can somehow determine both the values of Y and Z at compile time, which is pretty dubious. So even with sophisticated data flow techniques, aliasing can cause a compiler to have to err on the conservative side, and instead of putting store register 6B here, first have to put another load statement like that, which is going to slow down your program. So just be aware, when you do, pointers are very powerful. They allow us to implement all kinds of linked structures like linked lists and trees, but they do come with issues that impede the optimization of code, in addition to potentially having dangling pointers and memory leaks. Although with garbage collection, we can take care of these two problems, and we'll talk about that in a separate lecture. Now, the final topic we're going to talk about is operator overloading, which is kind of another issue that comes with the idea of bindings and knowing what binding is in is in effect. And you're used to operator overloading in C++, where, for example, the plus operator can be overloaded. So for a string, plus means concatenation, but for integers it means arithmetic. Or another common thing to overload in C++ is the output operator. For a class, you may define the output operator to print the contents of the class in a pretty fashion. But you can overload just about any operator in C++. Whereas in Java you can't, because the designers of Java decided it was too confusing and led to too many problems with code reading and code maintenance. That said, there are two types of operator overloading. The first type is called prefix overloading, and the second type is called infix overloading. And you're familiar, should be familiar with both types. So in C++, I could define a language or a class, let's call it complex, for a complex number. And we might say it has two components, a real component and an imaginary component. And then we may want to define a way to add to complex numbers. So we might say that we have complex operator plus takes a complex number, say V, and we might have it do something such as return complex real plus V dot real, and we'll say imaginary plus V dot imaginary. So this is an example of prefix overloading, because this will work fine if we have, say, three complex numbers, call them A, B, and C, and we can say something like C equals A plus B, and what that really gets translated to is C equals operator is A dot operator plus, and with a call to B. So that is the actual translation right here that the compiler makes. It's actually going to say A dot operator plus gets B as a parameter. So this works fine for complex numbers, but what happens in the case of a string? Let's say we have a string. Say we have a string and we say lname equals van der Zanden, and we say string name equals Brad plus lname. Now prefix overloading doesn't work so well, because this entity right here is really a char star, and that doesn't have any meaning. We would have been fine if we had written it as lname plus Brad, because then we could have had this really being lname dot operator plus Brad, and that would be okay. So prefix doesn't handle the case where the left operator or left argument might not be an object of the appropriate type. So then we can go back and we can use infix overloading. And that is done outside of any class. And you've probably seen an example. So here we'll say outside of any class, string operator plus takes a char star operand, call it op1, and a string as its operand 2. And then we could do something, for example, like this: return string op1 plus op2. And that will create a string object, and then it will invoke the infix operator, and all will be well. The last thing we're going to talk about is binding of reference environments, and we're going to put off most of the discussion for this until we get to functional languages. But there is one point that should be discussed now because you've seen it in Java. So remember that the reference environment is a set of bindings in effect when a function executes. And remember that there has been a case where you had something like this. You had main in Java, and you had string args, and then you had Java x.swing .invoke later, and you had some runnable, which I'm just going to say new runnable. And I'm going to have blah, blah, blah. But one of the things that you did is you tried to say run, or you had a function run. And inside that function, you tried to call a new, say, a, passing it args. Okay, so what you were doing is you were creating a function here that was going to execute after main had exited. So you have a reference environment issue. You want to execute this function here, yet main no longer exists. So you want to keep this binding of args to whatever values it has. And the way that Java handles this problem is you had to declare it as final. What that did is told Java that it's a constant. Remember, final is like saying something is a constant. Well, now that it's a constant, it's allowed to copy this value for args, and it can specifically put that into either a constant area or into the actual class here that we're creating, this anonymous class for runnable. It can create an area in it that will have the copied value of args. And since it's a constant and can't be modified, it's safe to do that copying and keep the value of args around. So that's the reason that Java requires that you declare something as final. If you could in some way modify args, and let's say you could modify it inside an if-then-else statement, then there's some uncertainty as to what really this value should be when we actually invoke run. Basically, the compiler wants some certainty on what's going to happen, and therefore it requires us to require anything or any local variable that we access here as being final.